By the end of this video, you should know applications of math outside of math and be able to do area and volume transformations. Today we'll be talking about the word ratio. All that ratio means is a fraction that relates two quantities. Okay. It is from the Latin ratio, and ratio means a calculation or a reckoning. And speaking of a reckoning, there's a little video by Hosking Stubenhofer Productions I'd like to show you now. Hey, Big Country K, I reckon my hat's bigger than yours with a ratio of 10/1. Huh?
Yeah.
You reckon?
Yeah. I reckon it's my hat now.
Oh! That was interesting. Another interesting thing is an interesting ratio about stars to people. Did you know there are 10 to the 24th stars in the universe, estimated, and about 7 billion people in the world? So crunching a few numbers, you can see there are 140 trillion stars for every person. And I took the time to draw that. No, I didn't. That'd be a lot of stars, though. There's three different ways we could say that ratio. 140 trillion to 1, that's in words. 140 trillion to 1, using that colon, that's usually called odds. And 140 trillion over 1 as a fraction, and that's the one we'll be talking about today. Another example of ratio is from the YouTube video Charlie Bit Me. I don't actually have the video, but I think probably about everybody in the world has seen it 4 times. Some ratios from that. Let's see if you can figure them out. Baldies to not baldies, what's the ratio? It is 1 to 1. Whoa. Let's go over here. Biters to bitten. What's the ratio? Again, 1 to 1. There was one biter, there he is, Charlie, and one bitten, other kid, I don't know his name. Girls to boys, what's the ratio? 0/2. There were no girls. And, shoot, that one was out of place. Humans to dragons. Pretend you didn't see it. 2/1. You might be saying, what? There were no dragons in there. Well, think again. You didn't look carefully enough. That's from Shrek. Alright, let's do, here. Do you notice anything about these shapes? A relationship between the two? Hopefully you do. They are similar shapes, which just means one is a bigger version of the other. The bigger one is twice as big. So if the big one was Dr. Evil, the smaller version would be, Mini-Me. It's kind of like that. Alright, so let's just look at the side lengths and the ratio of them. Big over little, we could say it is 6/3, which is 2. We could have also done it the other way, with the 2 and the 4. We still would have gotten the same answer. Alright, so we could say the ratio of the side lengths is 2. Now let's look at the areas of the rectangles. Okay, the space inside them, how much space they take up. 2-dimensional. Alright, and the ratio there. Big over little would be, well, when you figure out the areas, the small one is 6, 2 times 3, and the big one's 24, because of 4 times 6. So 24/6 gives us 4. So the ratio of the areas is 4. And you might be saying, hey, what the heck? The ratio of the side lengths was 2. Why is the ratio of the areas 4? Okay, we have this situation. Why is that? Well, we'll talk about that here in a minute, and also answer the question, what is the ratio of the volumes? Well, maybe you already know that. Let's talk about the areas first, though. The area of the small one, length times width, was 2 times 3, and we got 6. Now, that's because for the bigger one, we doubled the length and the width. So our formula is going to be real similar. Our equation will be really similar with the 2 times 3, except we doubled there and we doubled there. So we got to throw a couple 2's in there. And when you put 2 2's in there, multiply them, you get a 2 squared, we get a 4 out. Okay? So the little one was 6, the big one's going to be 4 times 6, so it'll be 4 times bigger. That's why the ratio of the areas was 4. Alright, check. Now let's talk about what the volume ratio would be. Maybe you can take a guess at it. I'm going to make these 3D. Boom! Let's just say the depth there is 4, and for the big one 8. So we keep the doubling going on. What would be the ratio of the volumes? Well, the little one, length times width times height, would get us 24. And the formula for the big one would be real similar. A 2, a 3, and a 4 in there, but we doubled everything. So in the equation, we have to double everything. When you have 3 2's multiplied together, you get 2 to the third, and 2 to the third is 8. Okay, so the volume will be 8 times bigger. Maybe you notice here that for side lengths, areas, and volumes, we really have 2 to the first, 2 to the second, and 2 to the third. Okay, that doesn't just work for 2, it works for everything. Some other examples, if we would have done the big one 3 times bigger, we would have had 3, 9, and 27. If we would have made the big rectangle 10 times bigger, we would have had 10, 100, and 1,000. If we would have just said x times bigger, x to the first, x squared, and x to the third, or x cubed. Alright? Now you might be asking yourself, does this only work with rectangular shapes? Your answer? No. It also works with some other things. It also works with, you could say, pyramids or cones. Be quiet, Izzy. It also works with tree trunks. It also works with tree trunks. Basically, all three-dimensional shapes, it works with those. Okay, for example, spheres, we haven't talked about them. Does anybody know what the diameter ratio would be here? You could say 1.5 or just 15 over 10. We'll leave it as a fraction. Thinking back to earlier, what would then be the area ratio, the surface area? Be 15 over 10 squared. I bet you'll get this one. What would be the ratio of the volumes of these spheres? 15 over 10 cubed. Alright? Just like the pattern from earlier. Alright, I think you're ready. Here's problem 1. An architect is designing a 2-story house. The architect's first drawing shows a rectangular staircase in the living room. In a second drawing, the architect is going to move the staircase across a wall into the entry hall. The amount of floor space the staircase takes up before the move is 60 square feet. The amount of floor space the staircase takes up after the move is blank. Alright? See if you can figure that out. I'll give you about 5 seconds. And you can pause it if you want, otherwise, here's a spoiler. Well, the architect is designing a 2-story house, and he or she draws a rectangular staircase. So there's what that would look like. In a second drawing, the architect is going to move the staircase across the wall. Okay, that's pretty simple. We just move it over there. The amount of floor space the staircase takes up before the move is 60 square feet. I noted that in yellow there. And we're trying to figure out how much it would take up after the move. Alright? Well, all we did was move the staircase, so will the square feet change? I don't think so. There was no change in size at all. Okay? So the answer is just B. That was kind of tricky because it was so easy. Alright, that was problem 1. Here's problem 2. I know what you're thinking. There's so much going on in this problem, but let's just look at it one chunk at a time. A company that makes roller bearings has a contract for a new, bigger bearing design. The new design requires changing the dimensions of an existing bearing design as shown in the diagram below. There's the picture. The old one is the little one, and they're making a larger one apparently. And I labeled the lengths of the length and the radius there. Alright, both designs are right circular cylinders. Don't get confused by that. All that means is it's a regular, like a can of soup, not some tilted cylinder thing. Alright? Which statement describes the relationship between the volumes of the new bearing and the original bearing? And then it gives us 4 choices. 4, 42, 64, or 2 times 4, bigger. Okay, so go ahead and decide on that. Otherwise, spoiler alert, if we look at the sides, they all got 4 times bigger. We know that means the surface area of these cylinders would be 4 squared, or 16 times bigger for the bigger one. And the volume would then be how many times larger? 4 to the third. Okay, hopefully you can see the pattern with the 4's there. And 4 to the third is 64. So the answer for that one is C.